Welcome back to the second part of Hall effect angle sensors, or as they are also sometimes called, Hall effect rotary position sensors. Anyway, in the first part we had a look at the theory, the working principles of these things, and we did some experiments here with that little test jig. You can't probably read it back there, but there's the angle displayed, the angular position of that little Lego wheel here. Card here, link in the description. In this part, this will be a lot more drier because we have now a look at the circuitry on my breadboard here with the Arduino. Look at the circuitry here on the breakout board with the actual angle sensor. And we will, of course, go over all the code that makes the thing work. And yeah, in parallel, have a look at the oscilloscope, at what's going on the SPI bus. Enjoy! Let's start with the circuit on the breakout board. There you find, of course, the A1334 Hall effect angle sensor and two decoupling capacitors, one for VCC and one for a pin called bypass. The reason for that bypass pin with another decoupling capacitor is that this thing internally has a 3.3 volt voltage regulator. All the digital interface of that thing is 3.3 volts, not 5 volts. Supply voltage can be somewhere between, I think, 4.5 volts to 36 volts. We have a look at the datasheet in a second. Anyway, the output of that 3.3 volt internal regulator is decoupled by that external capacitor. Yeah, and on the other side, you have your usual SPI stuff. Chip select, MOSI, clock, master in, slave out. Yeah, and that's it. You have also a differentiation between analog ground and the digital ground, but you can put all grounds together. The chip itself has 14 pins. Most of them are double here. D ground, D ground, A ground, A ground, another A ground, two VCCs. Yeah, you get the picture. A lot of pins, but not much functionality. And yeah, the SPI and of course ground and VCC go to my flat flex cable and to the breadboard with the Arduino. So here comes the flat flex cable to my breadboard with the Arduino Nano and 6 resistors. And that's how the circuit on my breadboard looks like. So here's the flat flex connection and the master in slave out from our A1334 on the breakout board goes here into the D12 meso pin of the Arduino, of course, and the master out slave in pin and the chip select pin and the slave clock pin from the Arduino. They go all through resistor voltage dividers to the MOSI chip select and slave clock pin of the A1334. We have also, of course, the 5 volt connection and the ground connection. And these voltage dividers just shift down the 5 volt signal levels from our 5 volt Arduino to the 3.3 volt signal level the A1334 expects. We do no level shifting here. We just take the 3.3 volt signal on the meso line and feed it in our 5 volt input. Usually that works. If you want to know details about connecting a 3.3 volt SPI device to a 5 volt Arduino, I explained that in detail in a video where I use a max thermocouple chip, which is also a 3.3 volt SPI device. Card here, link in the description. I guess it's time to go over the code, and I would love to say that this will be a quick thing, but it won't. There's a whole lot of stuff going on here. Of course, we need to include our SPI library, and I won't go into the basics of SPI programming. I've already done that in another Max thermocouple video. I will put a card up here and a link or links or cards in the description. Anyway, we have to define our A1334 pins. So first, how many A1334s are at our bus, and then in an array, the chip select pins for these chips. Ours is at digital pin 10. Then I'll define 3 read-write commands for the A1334. These read-write commands read and write internal registers of the chip, and there are a whole lot of registers, believe me. For absolute minimum bare bone operation, you need to read the Angel output register, and you need absolutely to write the control register. Yeah, to have a little bit information of what's going on inside that thing, you probably also want to read the error register. These commands have all the same format. First, most significant bit is read-write. Then we have a sync bit, which is always 0. Then we have the register address. These are obviously 6 bits here. And we have the data, if it's a write command, that we want to write to the register. So 7 bits, 1 byte. So our first command, as I said, is Angel output. That's very simple because the whole command word and the A1334 always accepts only 16-bit data transmission via SPI. It's all 0. Yeah, to read the error, we set this bit that should be number 2. This is out of alignment. Sorry. Number 2. Yeah, number 2 to 1. And if we want to read number 8 control, number 2 is of course 4. Number 8 control is bit 3. Okay. Now to the bits in the different registers. We have here 2 or 3 general data bits. So the most significant bit in every data transmission that comes from the A1334 is a general error flag. So if that is set, something went wrong. Then we have a undervoltage warning flag, and at the very end we have a parity bit. So the valid data bits are all other bits. That's what we are really getting back when reading data from the chip. Then we have for the error register a whole slew of error bits. And you see them here. I set them in the mask. So we have an EEPROM error, 2 EEPROM error, 1 temperature out of range internal error, target magnet lost, and low mode supply lost, a low power mode supply lost. And it's very important, this, once that error bit is set, the chip will stop working until you reset that error via the control register. And that's why you need at least, at the very minimum, the Angel read and the control write. The error read really is just for information. There are 24 more commands that you can send to the chip. Okay. Register write bits. In the control register there is a RPM bit. that where you can configure if the chip should be optimizing its readings for high or low RPM, and really important, the error flags reset. Whenever you encounter an error, yeah, especially a low power error, and you will encounter that error as soon as you power the chip up, because he comes from 0 volt to something and he says, oh, I was low power. I do know nothing until you tell me to. So yeah, you need to send this flag to the control register, and that's why we need that control write command here. Okay, that's just where the data is within the 16-bit words coming back. You see here I had these data bits defined, and they are offset 1 from the write. And yeah, I just have a constant for that, so I don't have a hard-coded 1 shift right somewhere in my code. Then the SPI mode. I never talked about that before, so let's do this in this video. So the Arduino knows 4 different SPI modes, 0 to 3. And these are basically all permutations between is your clock signal idle low or idle high, and is the capture edge, that is if you capture data on the data line on the rising or the falling edge of your clock. Yeah. 0 low rising, 1 low falling, 2 high falling, 3 high rising. So, and now we can do our SPI settings for our A1334, and I'm going very slow because you saw that I have a very long cable on for an SPI bus here, just with 100 kilohertz. And I do most significant bit first transmissions, and I'm using SPI mode 3. Remember, that was clock idle low, capture rise 3. How do I know to use SPI mode 3? You have a look into the data sheet. It's also somewhere in the text, but it's very, let's say, distributed. You won't find a sentence saying, okay, this chip is using SPI mode 3. And you won't even see a sentence or table where it says, okay, clock idle is high and we're sampling at the rising edge. But looking at the timing diagrams here, you see the clock before the chip select goes low is high, so clock idle high, and they made here these little lines into the diagram indicating that at the rising edge of the clock signal they will sample the data. And then we go into the setup, and that's run-of-the-mill SPI, nothing new here. I loop through all my chips connected to the SPI bus. I set the chip select pins as output, and I write high to the chip select pins, disabling all chips on the bus. I do an SPI begin, and then I do a serial begin with 1 megabit because I'm printing something out on the serial monitor or serial plotter. Then we continue with the loop, which is also quite simple. I have a delay 250. I loop through all my chips and I do a serial print of a function A1134 read angle, A1134 chip select pin. Simple. And then here's another parameter that's fixed true. This, you can already see it here, is verbose or non-verbose mode. After each chip, I print a tabulator, so it would look nice in the serial plotter. And after all chips are done, I'm printing a carriage return new line, print ln. Okay, read angle. Stop. After cutting the video, I noticed that the next 15 minutes of software walkthrough appear a little bit unstructured if you don't have an overview beforehand. So here it is. I structured the software in 3 layers. An application layer, which does really interesting things like read angle and read and reset errors. And that is built on top of the register level, where we have 2 main primitive functions, read register and write register. And that again is based on our bottom level, the SPI level, where we actually do SPI communication using the SPI transaction function. Each level has associated, that's not so clear to which level they belong, associated helper function at the SPI level, for example, something to check the parity of the data. And here on the application level, something to print data errors, to print the error register content out, and to decode the angle register. Don't ask me why the print data errors function don't have A1334 in front of it. And in the following, I will explain all functions from top to bottom. Let's get to it. There's a little more going on here. So we already know we get the chip select pin of the A1334 and this verbose boolean. I have unsigned int 16-bit data, which I'm handling with these chips. And I have, we saw that before, a general error flag and an undervoltage warning flag that I get with every communication with the chip. Then I call a function A1334 read register with a chip select pin, my bit mask for the command angel read. The data I will get back because it's a read register, and also to booleans I'm passing here, or getting back, I'm passing here only the reference for the general error and undervoltage warning flag. If there is a data transmission error, the parity bit is wrong. Yeah, we saw that also above. Then I simply print out in verbose mode parity error. Otherwise, I return not a number. If at least the data transmission was correct, I check for the general error flag and the undervoltage warning flag. And if neither of them are set, I return with another function here, A1134, decode angel register, the angle decoded in the data I got back from the chip via the read register function. Otherwise, if I'm verbose, I print these errors out, nicely formatted. And then, very important, I do an A1334 read and reset errors. Chip select verbose. I said before, if any error bits are set, especially that low power bit, you have to reset it to get the chip working again. And of course, in this case, I also return not a number. So next we have that ominous A1334 read and reset errors function, chip select pin and the boolean verbose. As usual, every function will have that. I have my 16-bit data variable here. I have again general error and undervoltage warning. And the first thing I do here is I read the error register. Yeah, the other parameters are the same. Read register, we saw that already before, and also the same if it's a general error, I print them out. If that function returns Parity bit error, I go here into the second part and say parity error. Yeah, nothing new here. And finally, if we are verbose and everything was okay in the data transmission and so on, I print also the error register information. This is really just verbose stuff, so you can see what's going on. Next, I write a register, okay? And chip select pin, there's no data returned here, but you already guessed it. I'm writing the control register, and within the control register, I'm writing the error reset. But of course, the chip is continually returning data, so I can also get here a general error and an undervoltage warning. Yeah, if something goes wrong, I just print it out, or a communication error. I'm just a bit thorough here. So further down, print errors, trivial. I just get these general error and Boolean undervoltage warning, and I nicely format them and print them out. A113 decode angel register, we used that. We just passed that the 16-bit data we get from the chip, and yeah, here I do first data and binary AND, the mask for the data bits. Then I shift it to the right with the other constant I defined, A1134 data shift right. And then I divide that with the data bits, data shift right. So I take the whole mask and put it to the very right plus 1. That's basically the range in bits or in integers of the angel register. And I multiply that, of course, because that's a fraction with 360 degrees. Another trivial function follows print error registers. Yeah, I defined all my register bits, and I can give that function the 16-bit data word, and it will print it out in a very nice manner. Now it will get a little bit, no, not that complicated. I have here my primitive write register function that gets chip select pin and the 16-bit command word I want to send via SPI, and it also returns general error or undervoltage warning, or is false as a result if I have another error. So here's my return data, 16-bit word, and I call another even more primitive, and now we're really at the low level, A113 SPI transaction. That function will return false if there is a communication error, that is a parity error. It gets chip select, the command, the return data, and the general error and undervoltage warning flags are just passed through. Same, or let's say similar, is the read register. It gets the same parameters plus returned data, not only the command. And it does also an SPI transaction, but it does two SPI transactions. Okay, in the first SPI transaction, chip select pin, the command, the return data, general error, undervoltage warning, all passed through. But then I do exactly the same again. I send the same command, and this time, this time is what counts in respect to the return data, and the first call is what counts in respect to the command I want to send. And of course I return if there was a communication error. That's a little bit lazy, okay, just from the last SPI transaction. Now, why do I need to send the command in one word and then get the return data in another? That's not really unique to the A1334. It's a feature of all SPI chips that have bidirectional data communication. That is, that are using the master out slave in line and the master in slave out line. And what happens is the chip select goes low, the clock starts ticking, controlled by the master, and with each clock signal, the chip shifts into an internal register the signal at the master out slave inline. But at the same time, it shifts out another internal register to the master in slave out line. So it goes at the same time, like, sorry for all female viewers, like two women talking. The problem is that when you send a command, you get not the data for that command, but you get the data for the previous command you sent. And that's the reason I'm first sending here the command. I could send anything here, in the second SPI transaction. But I first send the command and I get some data back, which I totally disregard because I don't know what command I sent before. And then I do another SPI transaction, pumping in 16-bit, getting out 16-bit. And this time, that's the return data that really counts. This is basically called stateless programming because I'm playing it safe. I always send first the command and then I send the command again, or it doesn't really matter what I send the second time. I send the command first and then I do another 16-bit data transfer and get the data for that command back from the chip. You could optimize that simply by caching somewhere which was the command I sent last. And if that matches the command you want to send, you can skip this part and go directly to the SPI transaction, which really reads your return data. And that leaves us with some more. Sorry. That leaves us with the SPI transaction itself, but that's standard SPI stuff, almost. So I begin my transaction. I set my chip select pin low. I get the return data from SPI.transfer16 because we always need to send and receive 16 bits. There's also the normal transfer, which transfers only 8 bits, but that's convenient here. Send at the same time the command, at the same time. Set my chip select pin high again, and I end the SPI transaction just in case somebody else or some other code wants to do some SPI stuff. I look if the general error flag is set. That was my bit mask constant in the return data. And I check the same for the undervoltage flag. And then I check if the parity is actually okay. And if not, I return false. Something went wrong in the communication completely. That leaves us just with the parity OK function, which simply checks the parity bit. I have two variables here, and please note this is not a high performance parity check function. It's more written for readability than performance. I have here a byte that indicates the position of the bit I'm currently checking or counting. I shouldn't have named that checking, and the numbers of bits set. I need that, of course, to calculate my parity. So this is initially 0, and then I go through all the bits from 0 to 15. And I simply have a bit mask here, so the least significant bit set, and I shift that to the left by my counter here. And I do a logical AND with the data which I'm checking, and I'm masking out here the parity bit itself. So logical NOT and the data. And if that is non-zero, so I have a bit set, but for the parity set bit itself, I increment my bit set variable. And at the very end, I check if my bit set variable is, the number in there is uneven. Modulo 2, there's still a remainder of 1. If it would be even, the remainder would be 0. If that is equal to, the parity bit is set, then I return true, otherwise I return false. Something wrong with the parity. That's the code. A nice code this time for a change. I put a little bit of effort to it to break it down in really small digestible functions. And of course, I will upload that to my Google Drive, and there will be a link in the description to that. That's it for today. I know I promised in the beginning that we would have a look at the oscilloscope, but with all that code walkthrough, the video got long enough as it is. And I mentioned that in the first part. I'm pressed for time right now, so we will defer the oscilloscope stuff to part 3. Promise. Till then, bye.